Okay, in this lecture we're going to go through a couple of basic cases with momentum. If time permits, we'll look into the relationship between momentum and energy and how they're different from each other. But first I just want to go into the very basics of how momentum works and how both mass and velocity affect it. Now mathematically we should be able to see that mass and velocity affect it equally. But that's not really the whole story, and I don't like to rely upon mathematics to be our way of understanding. So let's say that we have a person here, and the person is pushing a box. This brownish, tannish, off-whitish object is a box. And the box itself is extraordinarily light, massless in fact. But inside of the box is a ball. Kind of looks like a cabbage, but we'll treat it as a ball for now. And this ball has a mass m of, let's say, half of a kilogram. So we have a ball with half of a kilogram of mass. And this person pushes with a force on the box of, let's go with 2 newtons. So one of the things that we can do is we can try to figure out, well, if we push for a certain amount of time, how much momentum will this thing have? So let's just go through that. If this is the only force acting, we ignore frictional forces, or we say that this is the net force that the person is able to apply once we account for friction. So we have a force. Let's say that we have a change in time as well. We'll push for 2 seconds. That's going to equal the change in momentum of the object. So after 2 seconds of pushing with 2 newtons of force, we're going to have a change in momentum of 4 Newton seconds, or 4 kilograms times meters per second. Now, this tells us really what's going to happen to this object. If I look at momentum, the final momentum of this object, the initial was 0, let's say, so the initial velocity, we'll call that 0. But the final momentum of the system is going to be equal to m times v. And so what I can do is just take this 4 kilograms meters per second, divide by 0.5 kilograms, and we're left with 8 meters per second as the final velocity of this box with a single ball in it. So now I have an identical situation to this one, except that there are 4 balls inside of the massless box. So the total mass that this person has to push now are 2 kilograms. Still using 2 newtons of net force, still applying that force for 2 seconds. And so if we go over here, one of the things that we'll notice is that right off the bat, our change in momentum, the change in momentum for the system, is identical to what it was before, because we have the same force times the same change in time, 4 kilograms meters per second. So the momentum of this box will change by the same amount as the momentum of this one changed by. Where we get a difference is in the end result. Because there's more mass here, even though this is going to have the exact same momentum, so this one over here had 4 kilograms meters per second of momentum by the time it got up to speed, because it started with 0, this one's also going to have 4 kilograms meters per second. The same amount of motion will be occurring here as here. And so that gives us a velocity, in this case, of 4 divided by 2, or 2 meters per second. So what we get is 1/4 of the speed, but 4 times the mass. And that's really the trade-off that occurs with momentum. That's what it's about. The quantity of motion is interchangeable between mass and energy. The more mass you have, in order to have the same momentum, the less velocity you get. So here we had one ball, we got it up to 8 meters per second of speed, and it has a certain amount of momentum. It has a certain amount of motion for that object. If we include more objects, but we want to only have the same amount of motion going on, then each of the objects has to move less. There's your trade-off with momentum. So hopefully that kind of clarifies what momentum is, what it does. It's always measured from 0, like I said. So we're always basing it off of 0 motion. Well, this one has motion. It has 4 kilograms meters per second of motion. A 1 kilogram mass would be moving at 4 meters per second. A 20 kilogram mass would be moving at 1/5 of a meter per second. So there's always these trade-offs that occur with momentum. Now what we're going to do is we're going to take a look at a case of a bullet and an elephant, and we'll use those to clarify what happens with momentum and how it's different from what happens with energy.